Now we will learn about the LTE and EPC architecture, which is the Evolved Packet Core Architecture. The way we will cover it is through an example. That's always the best way to learn about any architecture. You're in a car and you're traveling from Istanbul to Izmir. These are two cities in Turkey, and it'll take you forever to get out of Istanbul traffic, so you're most of the time going to be just in the precincts of Istanbul. You're sitting with your friend who's driving and you are wanting to connect to the internet. What is the first thing that you're going to see? It will be a bunch of antennas and base stations that need to be provided to you all along the way on your way to Izmir. And these base stations and antennas, they are called E-node Bs or enhanced node base stations. So we love acronyms, and so we create acronyms for them, but these are essentially base stations that you are seeing. You're also wanting to connect to what's the internet, and for that you will need to have an IP address. So one way would be to give you an IP address at each of these base stations, but then your IP address would change as you keep going along. So the way the architecture works is that there is a gateway that gets created, which is called the P gateway, and your IP address is actually homed at this P gateway, and all your packets from the internet basically come to this IP address over here, and then from this P gateway the packets will make their way to the base stations. So one of the way to get your packets to your base station would be to connect P gateway to each of these base stations, and then your packets would come down this way. But this would also mean that every time you move from one base station to another base station, your path of the packet would have to be changed from the left to the right. And that would mean that every base station that you move would be visible to the P gateway. In order to move away from that, the architecture which was created was that there was another anchor that got added, and that anchor is called the serving gateway. The serving gateway is the one that is anchoring your mobility from one base station to the other, such that this mobility between these base stations is not visible to the packet gateway. Now the things that you've seen is we have drawn these lines which are showing the interfaces, that so-called the interfaces to the various nodes. And so these are the interfaces, that's one and this. And the way the architecture works, it calls each of these interfaces by a name. The interface name between the base station and the serving gateway is called S1U, and the interface between the serving gateway and P gateway is called S5. Another thing you will notice is I've shown solid lines and I've shown a dotted line. The solid line here is for what's called your data plane. So this is where your IP packet goes both ways. It'll go up, and then coming down from the internet will come down this way. And the dotted line over here is actually what's called a signaling interface. So there is some signaling traffic that also goes, and we will cover a little bit more about the signaling traffic in the next slide set. But the dotted line is not your data packet, but some signaling which we will cover when you go beyond a particular serving gateway. Now, so you've gotten your IP packet and they're able to go back and forth. Is this it? Is there something else which is missing? Yes, the most important part is how do you get access to this network? Not anybody can get access to this network, and in order to do that, you need to have some username and password, and you need to have a place where this username and password is stored. And that node is called the HSS. So that is your home subscriber subsystem, which stores your username and your password. And the details of this username and password, my writing skills are terrible with this pen, will be covered a little bit later. This is also your identity, as it's called, your identity, and your password and your other subscription data. So your subscription data is stored in this HSS over here. Now, in order for you to get authenticated, you will need to essentially send your credentials to the HSS. Now, here again, from if you had access the system through this E node B, your interface would have been through here. But then if you access it through another E node B, you would have to have an interface from there. So essentially, you could have an interface from each one of these base stations to your home subscriber subsystem to get yourself authenticated. This would again mean that as you kind of move from one base station to the other and you need to get re-authenticated over here, your HSS will see all this mobility, and the way the architecture was created was to hide this mobility and also limit the amount of traffic that goes to the HSS. In order to do that, what was created was this MME, which is called the Mobility Management Entity. These acronyms are there in the next slide. So at the moment, just bear with me. So this is the proxy entity for which all your authentication signaling and all your signaling from your base station goes to, and it is the one that then will request for your identity and request for your password validation from the HSS. So that's called your mobility management entity. There's actually one more interface that is from this mobility management entity, and that is for control of your handovers itself. And that interface is called the S11 interface. And this interface is primarily for handling mobility as you go from one base station to the other. This base station, when you come here, has to tell the serving gateway, look, I am serving this UE, please send any packets coming from the internet to the UE to me. But in order to do that, he doesn't have a direct signaling interface. So the way the signaling goes, the signaling will go via the MME, and then the MME will tell the serving gateway that, hey, look, this mobile is no longer at E node B1, he has moved to E node B2. So this S11 interface over here is meant for carrying signaling messages between the MME to control the serving gateway. This is pretty much close to what the architecture is. There's one more interface, and that is the interface between the base stations themselves, and this is used for handover. So when you move from this base station to this next base station, what happens is some of your internet packets may have already come down to this old base station in the meantime while you moved over here, and that packet is transferred from your old base station to the new base station. That's this solid blue line. The dotted blue line is again for signaling messages for this base station to tell this neighboring base station, hey, this mobile's coming, can you please handle him? And then this base station goes back to the source base station and tells, yes, I can handle him, and then the mobile essentially moves over to this base station. This is the core part of the EPC Evolved Packet Core or the LTE architecture. This is it. These are the main interfaces. These are the main network elements. We saw that the architecture was built of network elements, the serving gateway, P gateway, E node B, the mobility management entity, and the HSS, and a bunch of interfaces which are either signaling interfaces or user plane interfaces or data interfaces, and for each of these interfaces we give some interface name to them. S5 is the one between serving gateway and P gateway, and S5 includes both a user plane interface and a signaling interface. So now what happens, there's one more interface, and that we'll cover next, is now you've gotten out of Istanbul traffic, you're getting close to Manisa, now you're at this base station number 4. You will essentially have the same architecture as we had before, where you have a bunch of base stations that are connected to each other. They have an interface X2. You may or may not have an X2 interface between all base stations. In most cases, these interfaces are present between all base stations, so you could expect to have an interface like this, but I showed a general case where this interface does not exist. And your MME is the one, the mobility management entity, which is handling the mobility between these base stations, and it also has an interface to the HSS. Now, when you move from this base station to this base station, you needed to basically do a handover. And for that handover, there is yet another interface that is needed, and that's between these MMEs themselves, and that is this interface called S10 interface. So that is used when you go from one subset of base stations that are controlled by one MME to another MME which is controlling another set of base stations. And this interface over here is used for providing signaling messages that this UE is coming from this base station to the next base station, so please handle it, and also authentication information about the mobile. So this includes both signaling for handover, so this is both for handover and also for passing the user context. Okay, there we go. I could write that here and you can almost read it. And that is what your architecture is in general, the instantiation of an LTE architecture. Now, just for a few terminology that you will see quite a bit, there are two terms which are used. One is what's called the E-UTRAN, and that is your radio access network. And this includes your E-Node B. Another element that we hadn't talked about is the mobile itself, and the mobile is called a user equipment, UE, and this is a term you will see in specifications being used. And there is the interface between the mobile and the base station, which is called by the letter LTE UU, which is both includes a data plane that carries the user traffic and also a signaling for all the signaling about what is my power, I need to hand over, please connect me, please give me more, please hand me over to the next base station, here are my measurements. So these are a bunch of signaling messages that go between the mobile and the E-Node B. So you have the evolved E-UTRAN, which is a bunch of base stations and also includes your interface to your mobile, and then the rest of the architecture, which is called your evolved packet core, which is including all of your MMEs, your serving gateway, P gateway, and HSS, and that's called EPC. So whenever you see EPC, that's your core over here, and whenever you see E-UTRAN, that's your radio access network. Now, what is LTE? So now where is LTE? The thing is, LTE is actually a commercial term which is typically not used in the standards specifications themselves. To most people, the entire LTE system means this entire system, but as I said, this term is not really used in specifications. What you use is either the evolved packet core or the evolved UTRAN, which is evolved Universal Terrestrial Radio Access Network. We love acronyms, I'm sorry about that. And that is your architecture for your evolved packet system, as it is called. The typical diagram that you will see in specification actually looks like this, which on the first look doesn't give you any intuition as to how this network works, but for specifying the system, this is the terminology which gets used. And these diagrams are where you have your essentially your network elements, as they're called, your base station, your serving gateway, your P gateway, your MME. The number of these base stations that are there are not shown in this architecture diagram. What is shown is that you could have an interface between two E-Node Bs, and that's called the X2 interface. And we saw that you could also have an interface between two MMEs, and that's the S10 interface. So you do see this kind of a line drawn back to the same node itself, and that is specifying an interface between two of these instantiations of your mobility management entity. The lines between these network elements are called interfaces or reference points, and they can either be a single protocol, this one just has a data plane, or it could include both a user plane and also a control plane, but they are still called S5. Sometimes in order for people to refer to the user plane, they will call this the user plane as S5U, and for the control plane, they will refer to it as S5C. But the interface itself, both of these together are just called S5. And then you have interface out to the internet, which is SGI. Operators also have their own private network and where they offer you services. And here what the service means is things like VoLTE. So this will host any of your VoLTE servers that also interconnect through your packet gateway down to your mobile, which is on this side. Okay. At the high level, the network architecture in the specification actually consists of two main elements, which is your mobile on the left-hand side and your network on the right-hand side. The mobile on the left-hand side is actually broken up into two parts. One, which is your SIM card, or which is also called USIM, which includes your identity and your password. Your main identity of who you are is in your SIM card. So if you do not have a SIM card, you cannot connect to the network. Well, you get some connectivity only for emergency, and you also have your password, which is called your main key. So that is built into your SIM card, and then the other part, which is your mobile equipment, your phone, that is called the mobile equipment, and these two together are using the term user equipment, and that's what you will see everywhere in specification, the term UE together, which means both your SIM and your mobile equipment. On the network side, you essentially have a radio access network, which is your E node B, and your core network, which we saw was a combination of MME serving gateway, P gateway, and HSS. And this is what at the high level your RAN, as people keep referred to, and your core are, core network and RAN, radio access network. A key concept of the LTE architecture is roaming, and you will see this roaming support in specifications quite a lot. Well, what is roaming? You all know, well, roaming is essentially you can take your mobile phone if you're a subscriber of a Turkish operator, let's say Turkcell, and you go visiting your parents in the home, in your home country, for example, if that's India. You're able to make phone calls, you're able to browse the internet, though sometimes at a much more expensive rate, even when you're in India, without having to do something special on your side. And this support for roaming has been built into the 3GPP architectures right from the GSM days, and similar concepts have also been extended to LTE. What does roaming really require? It requires that when you are in India, that the operator is able to figure out which operator you belong to. So who is your home operator in one way. And in the internet days, you always kind of say, yes, what is your domain name in a way? So what's your domain name of your identity? So the way the identity is created of each individual, of each subscriber, it's in a way that it contains the domain name of the home operator. And in the LTE attached lecture, we look at what your identity that your network knows you by, and that contains your home operator's identity also in it. Apart from just identifying your home operator, also the visited operator or the visited country where you're in, and the visited operator needs to be able to authenticate you. So it should be able to get to where your subscription data is in your home country. The subscription data, your keys never leave your home country. So your passwords are always in your home network. And the most important thing from an operator point of view is obviously they want to be able to sharing the revenues, and a lot of times it's that expensive bill that you see on your phone when you're like, oh my god, is this so expensive? Sometimes you don't make calls, but nowadays the roaming charges are coming down. So the architecture kind of allows these things to happen, or enables these things to happen without a human intervention. And this has kind of impacts on the architecture itself. Let's take a look at what a non-roaming and roaming architecture would look like. And the non-roaming architecture is what we have seen so far. It's the usual concept that you are in your home network and all your network entities are in your home network. So this is in Turkey, this you're in Turkcell operator. All of these entities are in Turkey, in Turkcell's data centers. Of course, these are out in the field, and these are out in various data centers in Turkey. Now you're out visiting India, for example. You are in the visited network, it's called, so that's out in India. Your HSS, your subscription information, is still in Turkey. It never moves out of here. So the MME, which is out in India, will have to locate the your home domain from your identity. So when you attach, you will have to provide your identity. From your identity, the visited network figures out that you are actually a roamer, as it's called. You are a roamer, and it'll find out what your home HSS is and authenticate you from the home HSS. And also, one of the most common architectures, and this is an architecture which is called roaming with home routed traffic, is that your IP address and your P gateway is actually in the home. So this is roaming with home routed traffic. It's also called so that's what this architecture is primarily. And even though the architecture kind of, when you look at it, you say, this looks very similar to this, it's just where things are located. You may be right, but when we did develop the architecture, the whole concept that you needed to have a local anchor as an S gateway was essentially also driven a lot from a roaming architecture. So the need for this entity becomes much more apparent when you say that you don't want to show, or you don't want to be able to handle each and every base station change out in the home network. There are also things that when you look into the details, there are ways in which charging, or at least charging may not be at a user specific level, but at least at an aggregation level, also occurs in the serving gateway, in addition to the P gateway. So the home operator is doing your home charging, obviously, and is going to create your bill. The visited operator is also finding out, how many megabytes of traffic is actually going out to this home operator, so that I can bill the home operator. So that is inter-operator billing. So this visited operator bills the home operator saying, 17,000 of your subscribers came to my network, they used 45 megabytes, gigabytes, hand me over the money. So that's those are the key things there. There's also one more part in the roaming architecture, which we just kind of said. The first part was this home routed traffic, where your P gateway is in your home network, and there is a similar architecture where your traffic is actually being going out to the internet from the visited operator, and that's what's called roaming with local breakout. You'll see the term LBO being used in the specifications. That's local breakout. This architecture is primarily used for voice, because you don't have to go back all the way to your home network. I mean, India and Turkey is not that bad. Suppose you're in the United States and your traffic has to come all the way back to Turkey and then be able to go out to the internet. Most operators actually deploy this architecture today, and the main reason is that operators are are non-trusting of the non-trusting kind. They want to make sure that they are the ones who are owning your traffic, billing your traffic, making sure that they know exactly how many megabytes you have used when you are in the visited network, so that when you call up your operator and say, "Hey, I've got this huge bill. I didn't use the internet the way the way the bill says," and the operator will say, no, you did, or you didn't, and it's able to get the record rather than depend on the visited operator to provide the record. But if you're doing voice over IP kind of a traffic, then you want to make sure that you're able to get out to the internet and be able to talk to your correspondent node right away, and that's where the P gateway is in the visited network. So the key concepts of the LTE architecture are the following. One is that all radio-related functionality is pushed down to the base station. And that's all there in the E node B. For those people who are knowledgeable about the 3G architecture, we had another entity which was called the RNC, which was separated from the E node B, and we had two nodes, but now we are down to just one node, and all the functionality is down in the E node B. In the control plane, there is control plane and user plane separation. The MME is the control plane entity which does all the transaction related work. And then the S gateway, P gateway are user plane entities, and they carry the user's traffic. There is a little bit of a control plane signaling between the S gateway, P gateway, but for most practical purposes, these two nodes are essentially handling just the user plane traffic. One interesting thing is that LTE is a packet switch domain only, and there is a funny video that you can see on YouTube which talks about LTE not supporting voice. It's about Hitler kind of being made aware that LTE is not supporting voice, and he gets all furious. So if you've got some time, do a Google look at it, and it's a hilarious video. So there was at the time when LTE had come out, there were people who kind of had come out with this sign, essentially creating something which said something like this: voice is not supported, and which is not correct in the sense that voice is supported as voice over LTE, but what's called the CS domain, that is the way voice is today carried in 3GPP networks is in 3G networks is not supported, and it's what is going to be supported is voice over LTE, and that's called VoLTE.